Now let's move on to the differential equation that we built the previous lecture for. Consider this guy. Consider the fourth derivative of f plus 4 times beta to the power 4f equals 0. Beta is a positive number. It's 1, 2, 3. It's anything, but it is positive number. F, I would say f is defined on this domain from 0, and this point is pretty tricky because it goes all the way to infinity, right? Just if you can remember, the difference between a bracket and a parentheses is that when you put a bracket, that means that the domain includes that value 0, but when I put a parentheses, it means that it doesn't include that value. Infinity is not well defined, so that's why we put a parentheses. We're saying that the domain doesn't include infinity, but it goes very close to infinity. Okay. Now let me define the boundary conditions. The boundary conditions are pretty interesting. The first ones are the third derivative of at 0 equals 2, and the first derivative at 0 equals 0. But we want to have a boundary condition at the other end too. That one is pretty interesting. I would like to say that the value of the function f as we go close to infinity will become 0. So that's how I'll put it in the mathematical form. I would say, I want to say f as it goes to infinity becomes 0. So let me define, I will define a variable a. I will say I will take the limit of f at a as a goes to infinity. That's how I put it mathematically. I think it makes more sense. But that's what this guy is telling, that f goes to 0 at infinity. Now let's try to solve this differential equation. We're going to do the same thing that we did in the previous example. We're going to guess the form of the solution. Again, I'm going to guess the same form for the solution. I would say f is equal to an exponential function. The differential equation here is, oh wait a second, now you see the differential equation. It's fourth order, so I will have 4 constants. So I'll put them in this summation 4. So I will have 4 constants, and I'll say C, and let's say J. Okay, and J goes from 1 to 4. So there are going to be 4 constants times the exponential function e to the lambda jx. So J is going to be 1, 2, 3, and 4. Alright, now I'm going to insert this f into the differential equation up here, and I will get that equation. Let me show you how they look like before. It's going to be the same thing here too, but I don't want to write it out, so let me just show you. This is the previous example, this guy, and so I guess the form of the solution. This is essentially the same form that we guessed here. We inserted it into the differential equation, and we ended up with this equation here. Okay. So I'm not going to write out everything, but you can remember that in the middle something was appearing. It was the term that had to be, there was the only way that to make this whole equation, whole left hand side equal to 0, was to make this term in the middle equal to 0. I'm not going to write out everything, but here you can guess that if I put this function into the differential equation, I will end up with something which looked like just what we saw. Let me write it out. We will end up essentially with lambda j to the power 4, because we take the fourth derivative of an exponential function. I will end up with lambda to the power 4, and I'll have a plus 4 beta to the power 4, so it's going to be here too, equal 0. Okay, try that yourself. Put f into the differential equation and do the same thing that we did before and make sure that what I wrote here is correct. Okay, so let me take this guy to the other side. So lambda j to the power 4 would be equal to minus 4 times beta to the power 4. Alright, now this is pretty interesting. You see, beta is a positive number. So beta to the power 4 is also positive. 4 is a positive integer, so this whole thing here is positive, and it's multiplied by negative. So the entire term on the right hand side is a negative number. Now I'm going to take the fourth root of a negative number. And this is pretty tricky. I told you in the previous lecture, I told you that this is going to be, we need to do something special for it. And we also found the fourth root. So I'm just going to throw the answer at you, but go ahead and use the method that we used in the previous lecture to figure out the value of lambda yourself. But the answer would be like this. We'll have 4 lambdas, by the way. So j, there were 4 j's. J goes from 1 to 4, so we'll have 4 lambdas too, rest assured. Lambda 1 be equal to beta times 1 plus I. And I could write everything here. Yeah, I'll just write below it. Lambda 2 equal to minus beta 1 plus I. Lambda 3 be equal to beta times minus 1 plus I, and lambda 4 be equal to minus beta times minus 1 plus I. Okay, that's pretty amazing. I found 4 lambdas. Okay, so in this form of the solution that I guessed, lambdas are now known. I figure out what lambdas are. So the only unknown right now is C, and of course it's going to be an exercise for you guys to find C, but let's move on a little bit more to find at least the family of solution, because I think that's going to be interesting to see. Okay, so now what I'm going to do is to put these lambdas into this form of the equation that we guessed. Okay, here, just inserting it right away. So let me write out everything. Let's say, let me start from here. F be equal to C1 times e to the power beta times 1 plus I plus C2 times e to the power minus beta 1 plus I, and then plus C3 times e to the power beta times minus 1 plus I, and C4 times e to the power minus beta times minus 1 plus I. Okay, that's about it. That's a family of solution. That is pretty cool. A very long one though, but very interesting. But it has a whole lot of things that I'm not comfortable with. To begin with, we didn't have imaginary numbers anywhere in the differential equation. I mean, let me bring the differential equation up again. This guy here, there was no imaginary number here whatsoever. The boundary conditions, there was nothing imaginary about them either. And the domain, it was pretty damn real too. So why the heck did I ended up with a family of solution which has a whole lot of imaginary numbers here? This is really uncomfortable. So let's do something. Let us use the Euler's formula to expand each one of these terms into sines and cosines, and then we can probably figure out what to do, what to make out of this situation.